So yeah, so I'm gonna present like my recent work and also like my previous work with DAISY and with other galaxy surveys. Yeah, so in particular, I'm going to focus in this talk on two major experiments that are promising to revolutionize our view of cosmology. So the one on the left is the dark energy spectroscopic instrument, which will provide us with the best 3D map of the universe by collecting spectra for more than 5 million galaxies. And DAISY is like the first of a new generation of galaxy surveys that will improve our observation by an order of magnitude at least. And then on the other side, we have the Vera Rubin Observatory, or LSST, which is instead a telescope that is now being constructed in Chile. And over 10 years, we'll create this basically wide color movie of the southern sky by collecting imaging for billions of galaxies. And the reason why I'm interested in these two surveys in particular is because I'm interested in combining their data set, spectroscopic and imaging data set. Because the DAISY experiment will observe something called large-scale structure, while the LSST telescope will provide observation of what is called gravitational lensing. So let's have a look at each of these probes a little bit in detail. So what is the large-scale structure? According to our current paradigm, we have this galaxy distribution that is painting the underlying dark matter field. And therefore, if we want to study gravity, we can study how a modification to the theory of gravity would behave with matter individually. And this is done by using two probes. One is the redshift phase distortion. So when we observe the spectra of the galaxy, and then we want to build this 3D map of the universe, of the galaxy distribution, we actually observe the redshift of each galaxy. And then we translate this into a distance. But the redshift of each galaxy contains the cosmological redshift, so due to the expansion of the space-time, and also a sort of Doppler effect due to the peculiar motion of each galaxy. Therefore, when we translate this redshift into a distance, we have an apparent distortion of the structure that we observe. And this effect, in principle, is just a systematic error that can be annoying because we don't have access to the real distribution of galaxies. But at large scale, where we are able to model this effect, is actually a powerful test to measure gravity, to test gravity. This is because, so what happened at large scales, you can see it in this little diagram here, is that we have a coherent motion of galaxies that overflow towards overdense region and outflow under dense region. And while they are moving, they are forming the structure. So by looking at this galaxy motion, we actually have information of how the growth rate is in our universe. And because this is our source of this distortion. So in synthesis, we have galaxy motion that is linked to gravity. By looking at the redshift of each galaxy, we have access to this motion and we are able to test gravity. Then we have another probe and that is called baryon acoustic oscillation. This is a process that is happening in the very early universe where we have this plasma made of photon and baryon coupled together. Under the influence of the dark matter gravitational field, this plasma is generating pressure waves. And then this wave will propagate until something called recombination. By leaving like an imprint in the baryonic matter distribution. And that's why nowadays when we look, as you can see here in this figure, when we look at our galaxy distribution, we still see this feature in the galaxy distribution, which, for example, can be seen in the correlation function by seeing an excess of probability of seeing galaxy at this particular scale. Yeah, so looking instead of lensing. So lensing is given by the fact that the light rays from very distant galaxies are traveling towards the large-scale structure, so towards the macro distribution, and therefore get deviated while they travel towards us. So by studying lensing, we are actually studying how, if the theory of general relativity is wrong, how would a new theory of gravity interact with light? And then, yeah, here I just put like a very simplistic diagram of how lensing works. So we have this distant source that is sending light to us, and this light gets deflected through these lens galaxies that are between us and the source. And this effect can be distinguished in two different effects. One is the convergence, where we have the magnification of the image of the galaxies, so appear bigger. And then we have the shear, that is the distortion in a particular direction. And yeah, in cosmology, we are mainly interested on what is called weak lensing, where the effect of this distortion is about 1%. And this is because this effect can be linearized and can be actually modeled, and therefore can be used to test our cosmological model. But on the other side, having those distortion being so small, we want to make sure we have a lot of imaging of galaxies in order to get some statistical signal. And therefore, surveys like LSST are very good for this, because they will have this deep imaging, collecting spectra for like billions of galaxies. And they will have like a great signal for lensing. So as we said, like very briefly, when we combine this probe, like the large-scale structure as observed by DAISY, and the lensing observed by LSST or other major imaging surveys, of course, these probes together are able to allow us for a broader explanation of the theory of gravity. Then more formally, what happens is that if we want to model this galaxy motion and deflection of light, we can do so by perturbing our metric. And so we have these two potentials, C and phi, where in general relativity, these potentials are supposed to be equal. But this is not a necessary condition in a modified gravity scenario. Therefore, if we use cosmological observation, we can test the property of these two potentials and being able to understand if general relativity is correct or not. In particular, when we look at lensing, we are sensitive to the sum of these two potentials along the line of sight. And therefore, we measure this component. While when we look at the growth of the structure, we are looking at non-relativistic particles, so we are just sensitive to this C function, which is the Newtonian potential. Yeah, so we need both to test whether those are equivalent or not, and so general relativity is correct or not. So yeah, we want to combine this probe, and how is the ideal case to combine this probe? Well, first of all, we want to have an area of overlap so that we can make our cross correlation of the two samples. And at the same time, we wish that this redshift distribution is made where the lens are, of course, behind the source, sorry, in front of the source, otherwise there's no lensing signal. And this is just like a very, just a small sketch of what it can be. So we have our probability distribution of the photo Z, so photometric redshift, and then the spectroscopic sample. And this, for example, can be done with DAISY or BOSS, that is the current data set. And instead for the photometric surveys, we have KIDS, the Hyper-Subaru CAM or dark energy survey, and in the future, LSST that will provide this observation. And for the analysis that I have in mind, I will probably have around 1,000 square degrees, counting 1 million of spectroscopic redshift for the first year of DAISY assembly, and up to 10 to the 7, 10 to the 8 photometric galaxies. So there, we talk about like the theory now, but there are also other aspects why it's very powerful, a powerful way to test gravity combining these two probes. And for example, regarding systematic error, one example is the bias function. So when we look at the dark matter distribution, we actually have access only to the galaxy distribution, and we need to make an assumption of how this field is related to the underlying dark matter field. And this relation is non-trivial. It can be non-local, non-linear, depending on the scale. So by putting these bias parameters, we are actually weakening our constraint on the theory of interest, because we need to treat them as nuisance parameter in a large-scale structure-only analysis. So if instead we use the lensing, the weak lens, we have a direct access to the matter field, and therefore by combining these two probes together, we actually obtain tighter constraint of the growth of the structure on the other parameters. And conversely, when we look at the lensing, one of the main systematic in lensing is the unknown photometric distribution of source galaxies, because this photometric redshift, of course, is not precise as the spectroscopic redshift. But there is a recent study by Schneider in 2006. Well, it's not really recent, but there are more recent studies that show how by cross-correlating the spectroscopic sample and the photometric sample, we are able to reconstruct the full photometric galaxy distribution, so selection function. So basically, we are not like reconstructing the photometric redshift of each individual galaxies, but we are estimating very well the n of z, so the density distribution of galaxies. So, so as we said, why combining this probe? We have a better control of these systematic errors. We decrease the degeneracy between the parameters, so we obtain tighter constraint. And in terms of gravity, we study how gravity, a possible theory of gravity would behave with light and matter at the same time. And of course, our key question is try to answer what is causing this cosmic acceleration. So if it's due to either energy component or to a modified gravity. And we hope that this future observation will allow us to have enough signal to answer this question. So this is, I will go back to this later, but it's just to show what combining probes means in terms of modification of the light deflection and modification of the gravitational constant. So I'll go back here later. So at the same time, in my research, I work on something called data compression, in particular lossless data compression. And this is because, as we mentioned at the beginning, this future survey will collect an unprecedented volume of data. And therefore, it's a key task for every analysis that we'll do will be to have efficient algorithm and also improve the methodology we use to analyze the data, because we want to make sure we are able to maximize the scientific outcome. And in my research, I focus on this third aspect that is a little bit a combination of this first and second, which is finding strategy, how to compress the data without losing any scientific information relevant for our scientific goal. So what is data compression in simple words? Data compression means you have your data sample and you identify which component of your data are most sensitive to the physics you care about. And then you amplify those components with respect to other components of your data that instead mainly contribute to the noise. And therefore you are able to build your optimal estimator. And in particular, I use this strategy to combine efficiently galaxies that belong to different epochs in the evolution of the universe. And I will go back to this later. Just a very boring slide on how this optimal data compression work in a simple, for a simple case. So let's suppose we have like our data set X, and we say that this data set is Gaussian distributed and has a mean mu and a covariance C. And basically we are linearly compressing this data set into this new data set Y through this weight function. So this, how do we derive the right weight function here that allow us to preserve all the information about the cosmology, for example, that we care about into Y? So for a single parameter, we can just write the Fisher matrix element for the compressed sample. And this has two components. The first one depends on the derivative of the covariance matrix with respect to our parameter we are interested to measure. And the second one is that depends on the derivative of the mean of our sample with respect to the parameter of interest. So very briefly, in cosmology, we usually assume that we know the covariance matrix a priori, because either we measure it from MOX or we assume that doesn't vary that much with the parameters. And therefore, we can solve these by maximizing this Fisher matrix element. Basically, we are minimizing the expected error on our parameter of interest, and we get the weight function W that give us this maximization is composed by the inverse of the covariance matrix times the mean derived with respect our parameter theta. So why do we care about this optimal data compression? For DAISY, for example, we will have 35 million of galaxies spread over 11 billion years of cosmic history, which means that if we treat galaxies that belong to this epoch like equivalent then to galaxies that belong to this other epoch, we are actually neglecting the fact that the expansion of the universe vary during this between those two objects. So usually a traditional approach is tending to cut the sample in different redshift bins and repeat the same analysis in each of the redshift bin. And this is quite expensive because you're required to repeat your analysis in each bin, and especially for lensing or galaxy-galaxy lensing, where the covariance matrix is quite big, can be quite difficult to deal with this kind of scenario. So we are usually tending to reduce the number of bins and so losing information about our galaxy distribution. And at the same time, if we work in Fourier space, of course, by binning your sample in a smaller bin, you enhance the effect of the geometry of the survey, the so-called window function effect. So instead, if you use this lossless data compression, you can compress your data into your redshift direction while maintaining the sensitivity to the evolution of the underlying theory. And you're not required to repeat this analysis multiple times. And this method is therefore quite efficient computationally. And it's also very flexible and robust. There are like different studies that try to use this lossless data compression in a lot of different scenarios, and they all show how robust this technique can be. So during my PhD, as Hector know very well, I've been working on the EBOS survey, and in particular, I've been leading one of the projects to measure the growth rate of the structure. And it's the first time I applied this weighting technique. But in this scenario, I was working just with an individual probe, so just with a large-scale structure. So just like a quick overview, what EBOS is part of the Sloan collaboration and observed different kind of objects between 2014 and 2019. Together with BOSS, they represent the best 3D map of the universe, and they, with EBOS, detected the first time the baryon acoustic oscillation and such a high redshift, roughly 1.5 effective redshift, and also the first, no, not the first, one of the first measurement of the growth rate that is high in explored redshift. So on the left, we have the result as a EBOS collaboration, and this is like our measurement of the DR14 catalog. Of course, I didn't put the DR16 because I had to leave the collaboration. But yeah, so this is the detection using the quasar of this baryon acoustic oscillation using like a standard technique. And while here on the right, there is my measurement using this optimal weighting technique. So I use two different parameterization. Here I'm measuring this F sigma 8 parameter, which is nothing else than the growth rate of the structure times the amplitude of our fluctuation, and as a function of redshift. And as you can see, like I use two different parameterization that give me different constraints. And if you are interested in the future, we can go into details about each of these analyses. But This is compared with another binning technique, the one Hector and Gongbo did. So this brown and gray point. And it was showing already quite promising result. Of course, the EBO sample has not that much signal that you can really distinguish between what is working better and what is working not that good, not that well. But with DAISY, that will expand the EBO sample for a factor of 30. We hope to see actually that how this growth rate evolves, so by reconstructing the evolution of this quantity as a function of redshift. So in this second part, I will actually talk more about what I've been doing recently to combine lensing and clustering in an optimal way. But first of all, let me say how this analysis works. We have an analysis made of three a set of 2-point correlation function, where the first one is the angular galaxy lensing power spectrum, or tangential shear if we work in configuration space. So this quantity, this galaxy lensing power spectrum, CJK, is proportional to the cross power spectrum of the shear and the galaxy sample, with those two weight functions that are basically just two functions proportional to the PDF of the galaxy sample and the source sample. So this is basically the projected power spectrum integrated over the co-moving distance, which is measuring the correlation between this shear and the density of the lens in our sample. So imaging and spectroscopic data cross correlation. Then we have the galaxy power spectrum, which I think everyone here is familiar with, that is using galaxies as tracer to describe how the matter is distributed on different frequencies. This can be described by the angular power spectrum, so the CGG quantity, or the 3D power spectrum, PGG. And then the third 2-point correlation function is instead the cosmic shear, which is correlating the galaxy shapes at different scales. So either in Fourier or in configuration space. So how does it work, this optimal compression with, clustering and lensing combined together? So it's a little bit different than the individual probe approach, because in this way, in this case, we are interested in the cross correlation between those two quantities as well. So what we do, we create our data vector if we're working, for example, in Fourier space, where we have the first n bin corresponding to the galaxy power spectrum, and then the second n bins are the galaxy lensing power spectrum. And this is our X data set that we want to compress in a new data set by using this optimal weight. But the difference is that here, our optimal weight contains the covariance between those two quantities. And this is because if we just use build our estimator by using an optimal weight that is optimal for example, CGG only, and the other one is CJK only, it's not really true that those weights will be optimal when these two probes are combined together. Then, as I said before, those weights depend on our choice of the parameter of interest, and here the test I've been doing, they are using the sigma 8 parameter and the bias. So this is actually something that is not done, let's say, properly, also when we use just the clustering itself, because when we measure the clustering, we measure the monopole and the quadrupole, which are actually correlated, and but instead we just use the FKP weight that are derived using just the monopole as quantity. So it's not really true that the weight that are optimal for the monopole would be optimal for the monopole and quadrupole when those are combined together. But yeah, anyway, so this is just, that's why we are using this cross correlation in our weight. And this is a little bit the proof of these, because as you can see, this is the, so on the y-axis, I put the optimal weight for the CGG power spectrum and for the CJK power spectrum. So the difference between the green and red lines is that This is the optimal weight function when working just with the CGG statistic. And this is the optimal weight function that is instead accounting for the cross correlation between the two. So for CGG, there's not much difference, but for CJK, there's actually a quite evident difference, which means that if we were using just the green weight, which is optimal for CJK as, sorry, the galaxy density power spectrum as an individual probe, we would be suboptimal because we should instead use this weight. So to check how this method worked, we did like a proof of concept by testing these weighted analysis on log normal mocks. In particular, we compare this analysis with the uncompressed analysis, which is a tomography analysis, where we just have like a lot of redshift beams and the power spectrum in each of these. And we also compare with a wide beam analysis, which correspond in taking just like a wide redshift beam, measuring power spectrum inside and just not caring about any evolution. So we fit for the sigma 8 and bias parameters. And yeah, we build those log normal mocks to be able to kind of mimic the lens distribution of DAISY and the source distribution of DES, HSC, and KIDS that are very similar actually in terms of overlap with DAISY. So yeah, of course, let me just say that this is all on log normal mocks, so at power spectrum level, so we are not actually seeing the effect of the window function or other disadvantages, for example, related to an uncompressed analysis. So what we saw actually was very promising because the weighted, so the compressed analysis was preserving all the information contained in the original sample that is given by the green point here. And this is our weighted analysis for both bias and sigma 8. So the error is computed as the average of the best fit, because we're working with Gaussian samples that is work, the average of 1000 log norm mock, I think, yeah, 1000. So just the scatter of the best fit, which in a Gaussian situation correspond exactly to the posterior of each individual realization. And yeah, so what we noticed instead that was quite interesting is that if we just neglect all the evolution and we just measure the galaxy-galaxy lensing power spectrum and the galaxy-galaxy power spectrum in neglecting the evolution of the sample, we get biased result. So as you can see here, there is a systematic, we're not able to reproduce what was inside the mock, the log normal mock. So this amplitude systematic is actually very easy to explain, and it's due to the fact that these two power spectra are two different redshift kernels. This is because, as we see from the definition here, one is integrated over this QG that is proportional to the PDF of the lenses, and the other one is integrated over QG and QK that is proportional to PDF of lenses and sources. Therefore, what is happening is that the bias parameter as a function of redshift is affecting the amplitude of these two power spectra in a different way at the same redshift. So it's basically, in simple words, it's like the effective redshift of these two quantities is different, but when we combine them together, we are kind of imposing that they are the same redshift, and therefore we get this biased result. And this can be corrected by using a very thin tomographic redshift beams, because in that way you can see that this will basically simplify and those two quantities will become the same. So this is, sorry, I didn't explain, this is the bias term. There's a square here that shouldn't be here. Sorry about that. So this is a bias term as derived by using the CGG power spectrum, and this is the bias term derived by using the CJK power spectrum. So these two quantities are different, and that's why we get this bias result. And it's also biasing the sigma 8 measurement, so it's quite tricky. While the redshift weight, by maintaining the evolution to the sample, are able to solve this problem in an iterative way. So it's not like super easy as well, but you can see more details in the paper of me and Chris. I think is this one, 2020, is explained better there. Yeah, so okay, we set up our analysis. So we have three 2-point correlation function, and now we want to test gravity by using the first year assembly of DAISY combined with imaging survey that are already releasing their data set publicly. So hopefully by the time DAISY year 1 is out, we will be able to combine with all these three surveys. So how do we want to test GR? I chose a phenomenological approach because I couldn't really choose which model of gravity I wanted to test. So I decided to go into a phenomenological way by introducing these parameters sigma and mu that are basically modulating the two lensing and Newtonian potential, as you can see here. And in particular, this parameterization is quite convenient, as we use already in different work, because allow us to parameterize the scale and time dependence in a flexible way. For example, we can use, we can write these two quantities as proportional to the dark energy and the dark energy density. Yeah, and we have that this quantity sigma and mu, of course, will be 0 for general relativity. So we expect these two quantities to be 0 in the case of general relativity. And this is the forecast I made for the DAISY year 1, sorry, this is DAISY year 1, combined with HSC and LSSC. So HSC is just because I didn't want to write all the imaging survey here, but we will have this 1000 square degrees. So we expect something similar for DES and kids as well. And as you can see here, this is the current measurement of this quantity that is actually quite old. It was in 2013, the last plot I could find. So maybe there's something more recent because I think this wasn't using BOSS data. But anyway, this is a 10% constraint over these two quantities. And this work will actually give us a 1% measurement. So it's quite impressive. Already with HSC is very impressive. And then with LSST year 1, we will have 3000 square degree overlap. So this will be even tighter. And why do we bother so much? Well, the recent result of kids in 2020 confirmed this 2-3 sigma tension with Planck in the value of sigma 8 and omega m. And we still don't know what is causing this discrepancy. Maybe statistic or systematic error, or maybe some new physics that we still don't understand. And we also have this other quantity that we can use to test gravity that is called the amplitude ratio test. This is basically using the amplitude of the galaxy lensing divided for the amplitude of our RST, and it's described by this quantity. So our CJK is the galaxy lensing power spectrum, and then we have our projected clustering amplitude, and then the RST term is given by beta. And with, like, let's say some approximations in GR, we can predict, we can assume that this quantity is scale independent, and we can predict the redshift evolution of this quantity. And it goes as the, is proportional to the growth of the structure and the dark matter density, energy density. So it's quite interesting because it's a very simple equation. Of course, there are approximations, but especially by using this weighted technique, we're able to reconstruct this evolution in redshift. So it will be even more relevant. And yeah, these are just like the forecast that Chris made for this quantity. So has with future data set. So DAISY is the red band, and then with the Formos and LSST, we will have, like, this is the final SST. With DAISY, we will have even tighter constraint, which is very exciting because it means that we will really know better what we are dealing with. Yeah, so just to recap what I talked about today. So yeah, we are doing this data compression for lensing and clustering. In particular, I have in mind the DAISY year 1 assembly. So if you're interested actually in joining some of these projects, let me know, because I'm currently coordinating the cosmological analysis framework with Daisy, clustering and lensing analysis. So we need actually more people to do tests and participate in our mock challenge. In particular, I already published this first proof of concept on like a paper that is not a Daisy paper. So where this treatment of the redshift systematic is also explained better than I could do today. And with the Daisy working group instead, we are, as I said, working out what is the best way to do our analysis using all the tools built by DES people and other imaging survey people. And now we are at the stage of deciding how to build our covariance matrix, whether we want to use just mock or a hybrid approach or just the analytical covariance matrix. So that's quite like a live discussion. We have teleconf every Wednesday, and we will also have a European friendly teleconf very soon. And so if you're interested in participating in this, please let me know. And it will be great to have more people involved in this project. So yeah, I'll thank you for your attention. I'll leave you with kind of a optimistic timeline of these first tests of gravity. And if you have any question, I'm just here.